So in this part of the chapter, we're going to start to look at one of the most important electronic components, which is operational amplifiers. So in this chapter, the content that we going to try to accomplish is, the first one is to describe what is an operational amplifier is, by looking at its principles of operations and several characteristics. And then after having going through that part, we are going to try to analyze several cases of inverting and non-inverting operational amplifier, and to do so we'll do several exercises. So to begin with, what is an operational amplifier? So an operational amplifier is an active component, so not like the components that we've seen before, such as the resistor or capacitor. An operational amplifier is basically an IC, or what we call an integrated circuit, that is a large collection of individual electrical and electronic circuits integrated on a single silicon wafer. The basic component in if we want to look closer into an op-amp, operational amplifier, it is basically a combination of transistors. So transistors is also going to be viewed in a chapter in these courses as well. But back to operational amplifier. So op-amp in the early days of computers is the most important component, where it is the component that basically that help us in 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 executing a great number of operations. So operations such as addition, filtering, integration, all based on the properties of an ideal amplifiers, right? So next we're going to look at is, and here in this slide we're looking at basically the component of operational amplifier, where we have 8 terminals. They are numbered from 1 to 8, and the direction of the numbering 1 to 8 can be basically referred to the position of these little marks that are usually placed on the operational amplifiers, right? So if we look into the schematic diagram so this is the physical object, right? So for example, we can see that the marking that we've seen on the physical op-amp is basically these markings, and the numbering usually goes in this particular direction from 1 to 8, and these 8 terminals represent the things that's written over here. And in terms of schematic diagram, it can be presented as this. So the most important terminals, or the most important terminals are the one that's marked with number 2 and number 3, which is the inverting input and non-inverting input, and the output is on terminal number 6. It is where we have the output. The other terminals that we may have to pay attention to as well is the terminal number 7 and terminal number 4, which is basically the power supply that we need to supply to the operational amplifier to make it functioning, right? So now an ideal operational amplifier has several characteristics that makes it work. So these are again an ideal characteristic of operational amplifier, but of course it would be slightly different, but it's not usually very far from this. The first one is, we'll see later on the component what we mean by all this. So the first one is the infinite voltage gain is equals to infinity. The voltage gain is called AV. So what is voltage gain? Again, if you look at the names of it, it is called operational amplifier. So the basic task that it does is basically it amplifies signals. So if I have to draw an operational amplifier, the symbols that we've seen just now, it has 2 input and 1 output. So the other terminals we can neglect for a moment. So these 2 terminals are basically the input plus and minus. So here we have one is non-inverting terminal, the other one is inverting terminal, and here we have the output, right? So It is called operational amplifier because basically what happened is when we give an input to the operational amplifier, the output will be multiplication of the difference of the amplifier of the input. So it will be a gain A multiplied by a combination of the input. So the combination of the input, of course, it will depends later on how the operational amplifiers is mounted with with other components around it, right? But at the end, there will always be a gain, which is multiplied by the input that we put into the operational amplifier. So that's what we call the voltage gain. So in an ideal operational amplifier, we would have a voltage gain equals to infinity. So uh, infinity means really big. If we put if we put a small, so we would have a typical value of gain. If we have a small input, it will increase the output very highly. Another one is what we call the input impedance, Z in. The input impedance, or in terms of DC, we can, if it is a DC, we can call it as input resistance. It will be the same thing. Input impedance equals to infinity. So where is input impedance? Input impedance is basically the resistance or the impedance at the input of the operational amplifier, and the input here is infinity. What does it mean to have an infinity input? Having an infinity input means there will be no current that could get into the operational amplifier. No current will be able to get into the operational amplifier. So depending on the components that we put around the arrange around the operational amplifier, that we mount around the operational amplifier, it can do different operations. But nonetheless, there will be no current that can get into the operational amplifier because the impedance, input impedance, is infinity. And the next one, the next characteristic on number 3 of an ideal operational amplifier is it has an output impedance of 0. So output impedance is the impedance at the output here. It will be equals to 0. It means there will always be an output, right? There will be no problem in giving an output. However, of course, the ideal operational amplifier is can never be made because the device has limitations, so on. So the value, we will have a typical value, but nonetheless, the gain is very high. The input impedance is very high, and the output impedance is very low, close to 0. So this is how a typical value looks like, right? Um, this is a typical ranges of operational amplifier parameters. So the first one is the open loop gain. So the open loop gain A that we said just now is infinity. It usually ranges from 10 to the power 5 to 10 to the power 8, right? So the ideal values we said just now is infinity. As for the input resistance, it is also very high, ranging from 10 to the power 6 to 10 to the power 13 ohm. As for output resistance, it's not really 0. It's around 10 to 100 ohm, which is very small. And as for the supply voltage, so this is not a condition of supply voltage is not a characteristic of ideal amplifiers. So this basically depends on the construction of the IC, the operational amplifiers. It ranges from +5 -5 volts to +-24 volts, right? So this is the supply voltage that we need to give to the op amp. So basically an op amp, if you look at the symbol, we have 2 input, 1 output, and these 2 legs over here represent the supply voltage, basically Vs plus and Vs minus. So this is the range of that Vs plus and Vs minus, right? So as an active element, of course, as an active element, it has to be powered by a voltage supply. So that's the voltage supplies that we mentioned just now, Vs plus and Vs minus, or here is mentioned as I plus and I minus. So this is the supply. Although the power supplies are often ignored in an op amp, in op amp circuit diagrams, but the current must not be overlooked. So if we look here in a node inside, we rarely look at it in solving the problem, but if we really look to the details, the current are usually very small. I naught, I output at uh, at terminals number 6 is equal to I1 plus I2 plus I plus minus I minus. But nonetheless, this is we don't really look into this when we do calculations of the input output, because the thing that we're going to look later is more if we have a certain voltage in input in terminal 2, a certain voltage input in terminal 3, we'll try to figure out what is the voltage output at terminal 6, right? So depending on the configuration of the other elements, especially resistances that are put around the operational amplifiers and the way that's connected to the ground, we can have different configurations, operations that can be executed by amplifiers. So the first one that we're going to look at is what we call inverting amplifiers. So what happened in inverting amplifiers? There are between these two input terminals, we have to there's a name for these input terminals. The input terminals that mark with negative signs or negative terminal signs, this is what we call inverting input. So that's what we call inverting input or inverting terminals. And as for the parts or the terminals, input terminals that's assigned with the sign plus, this is what we call a non-inverting input, right? So now let's see what happened in this particular arrangement. So what happened here is that we have an input voltage here on this side, and then what we have is that of course at the bottom we have everything that is connected to the ground. So the non-inverting terminals or the non-inverting input is connected to the input voltage Vi, and in between them we have one resistance R1, and then there's there's a node that's separating the branch that goes into the non-inverting terminal into another resistance RF, and this RF is then connected to the output of the operational amplifier. Okay, so R1 in the non-inverting on the non-inverting terminal and RF on the output terminal. So RF it's called F because it's what we call the feedback resistance. It's also what we call the feedback branch, right? So we get the current from the branch to get back into the input. And as for the non-inverting terminal, we just connect it to the ground. So what happens if we have this kind of configuration? The first thing that we can see is that if we apply, uh, remember the first of all, we have to remember the characteristic of an ideal amplifier. So the main characteristic that we have to remember that will allow us to do calculation is that the input impedance Z in equals to infinity. So the input impedance here equals to infinity. That means that there will be no current that goes into the non-inverting input, right? Even if we have current that circulates coming out from Vi, it won't be able to come into the operational amplifier. So at this node that is called which we call node 1, we can write a KCL which is I1 equals to I2, because I that gets into the operational amplifier equals to 0. So I1, all the current that comes from the V input I1 will become I2 that goes into RF. So that's why here we write I1 equals to I2, and then as we don't know what I1 and I2 is, we will try um, to look into these parameters I1 and I2. And when we look at I1 and I2, I1 is basically the current that goes through resistance number 1. So if it is the current that goes through resistance number 1, by Ohm law, we know that it is VR1, the voltage across R1, divided by R1. And the voltage that goes across R1 is the difference potential between VI and V1. So I1 is VI minus V1 divided by R1. And as for I2, I2 is the current that goes across RF. So by Ohm law again, the there will be a voltage across RF, and this current I2 will be equals to the voltage across RF. So of course the voltage should be in opposite direction of the current. So we have VRF. Here previously we have VR1. So this whole thing is actually VR1, and this whole thing now is VRF. And VRF, what is VRF? VRF is the difference potential between this point 1 and this point at the output, right? This point 1 and this point at the output. So the difference between that point 1 and point of the output is basically V1 minus V0. So V0 is the output signal. So next, what we can do once we have this. So here we also know that basically V1 and V2 equals to 0 for an ideal operational amplifier. Let me explain this a bit. So basically we have inverting terminal, non-inverting terminal. We have basically the point V1 is this point here, we call it as V1, and the point V2 is the point in the non-inverting terminal that leads to that's connected to the mesh, right? And then we have the feedback over here. So we're not going to look at this first, but for this part we have R1, and then it's connected to a supply called VI, right? And we have ground here. So basically in an ideal operational amplifier, it says that the input impedance is 0. If input impedance is 0, that means there's no current getting in from V1 into the operational amplifier. What does this mean? It means that if there is no currents that circulates in between V1 and V2, it means V1 in between V1 and V2, they are basically the same potential. That's why we have V1 equals to V2. And we look at here, V2, what's the value of V2? V2 is directly connected to the ground, so voltage 2 is 0. Therefore, we have V1 equals to V2 equals to 0. So what we had previously, where VR1 is basically VI minus V1, we have V1 equals to 0, and here we have VRF equals to VO minus V1. Here V1 also is also 0, right? So now the equation have become this equation. So V input over R1 equals to minus V0 over RF. So where do we get this minus V0? So I have an error here. Basically, it's not VO minus VI. It's not V0 minus VO minus V1. It's V1 minus V0, because VRF, if we look at VRF, so we have basically here we have the point of V output, VO, and if you look at VRF, so this is VRF, voltage across the resistance RF. So VRF is basically the potential difference here, which is V1, minus the potential difference here, which is V0. So it's V1 minus V0, and we know that V1 equals to 0, so now it becomes minus V0 over RF. So if we rearrange the whole equation, then we'll get, because what we're looking for is basically the output voltage, V0. So now we get V0 equals to minus, so the minus comes from basically because the input is affected at the inverting terminals, minus RF over R1 multiplied by V input. So this is the input, and now we get here the output voltage. So it is inverting, minus, and we have a gain of RF over R1. RF over R1. the ratio between the feedback resistance and the R1 input resistance is the ratio of the gain. So the voltage gains, which is V0 over V1. So if we write V0 over V1, it is minus RF over R1. So this voltage gain, AV, is basically the gain that we get from this kind of configuration of input and resistance around the operational amplifiers, right? So that's why we call it an inverting operational amplifiers. So to conclude, an inverting operational amplifiers reverse the polarity. So if the input was positive, then our output will get a negative sign, right? And then we also have while amplifying it, it means it's minus with a certain gain, and here the gain is of course is equals to minus RF over R1. So that's inverting operational amplifier. So for example, if we have we take a case of application, right? So we have basically V out from what we found just now, V out or V0 equals to the gain is basically minus RF over R1 multiplied by V in, right? If we have R1 equals to 100 ohm and RF equals to 200 ohm, and we put on input in the inverting terminal 10 volts, then we will get basically at output V output of 20 volt. And here basically we have the gain of the operational amplifier, which is minus RF over R1. So the gain is basically it's minus 2. We got a gain of minus 2. So when at input we put, so basically when at input we put 10 volts. When we put into the operational amplifier, we will get an output of minus 20 volts, right? So there's a gain of amplification in the middle. And how about the current? So this is a simple exercise. If you want to find the current across R1, again, just to remind, to recall, R1 is basically is the name of the resistance that we put at the input terminal, the inverting terminals, right? If I have to redraw it again, so this is V0. So this is R1. If you want to calculate, so the current here, I in, the current that goes across R1. So now you just, what we need to do is just Ohm law. So we know that V R1 equals to R1 multiplied by I in. Therefore, if we want to find I in, it's equals to simply VR1 divided by R1, right? So VR1 is basically VI minus 0. If you look here, VR1 is V in. So what's VI here is V in my drawing here. It's V in. So this V is V in minus 0. Why 0? 0 is the voltage at this point. It is 0 divided by R1. So we'll get 10 over 100 because we had 100 ohm of resistance R1. It will give us an input current of 0.1 ampere. So this is one example of application, right? Example of application. So it means if we have an input 10 volt, we want to amplify it and reverse the signal. We use this kind of configuration, which is inverting operational amplifier. Here we have a problem that you can try to solve, and then we will turn this into a quiz. So it is basically, if I want to give a quick look into it, so basically what happened is we can already guess what kind of operational amplifier is it, because we have basically our V in of 40 millivolts put into the inverting terminals, and the non-inverting terminals basically is connected to the ground, so we would have a gain of minus RF over R1. So here RF is 15 kilo ohm and R1 is 5 kilo ohm. So that will allow us to find V output. If we look at previous demonstration, V output will be equals to minus RF over R1. So this is the amplification ratio multiplied by V in. So I'll let you try. You should find an answer of, so basically you should find an answer of the V output will be equals to minus 120 millivolt. So we have 40 millivolt in input, it will be transformed into minus 120 millivolts. So you amplify by the order of 3 and it inverts the signals. And in terms of current, if you do the calculation of the current through the feedback resistors, now this current is the current through RF, so it's the current that goes inside here. IRF will be equals to 8 microampere. So how do we calculate IRF? Against IRF, just by Ohm law, it will be equals to, so VRF equals to RF multiplied by IF. So I is just VRF divided by RF, right? There you go. So in the next slides, what we're going to look at is the second configuration of amplifiers that will lead us to an operation of summing. So it's addition the signal that we have in the input, right? So we'll see how it works. We'll go directly into the example. So the example is here. Basically, what we have is we have 3 input voltages. So the input voltages are, we call it as V1, V2, and V3. And let's imagine that we put V1, V2, and V3 in parallel, and they are all connected at this node. And we across so in the input branch of V1, V2, V3, we put a certain resistance R1, R2, and R3, and the current that goes across the resistance will be called I1, I2, and I3, right? And they are all gathered. So if we write KCL, basically it will produce a sum of I, which is I1 plus I2 plus I3. So it's explained here. And then that I will goes into the thing that we've seen in previous slide in inverting op amps, right? So it goes into the inverting terminal, and again the non-inverting terminal is just connected to the ground, and then again in connection from the non-inverting and the inverting to the output, will have a feedback resistance RF, right? So let's look at what we can calculate with this. The first thing is, at this point, we can write a KCL, which is I equals to I1 plus I2 plus I3. And then if we look further, because we don't know what the value of I1 is, I2 and I3, what are those values? So if we look case by case into each branch, I1, what is I1? I1 is basically the current that goes through the resistance 1, right? Again, Ohm law, if it is the current that goes through resistance 1, it means it is the voltage VR1 divided by R1. So this is basically VR1, voltage across R1. So what is it? It is VI. So voltage across VR1 is the difference potential between V1, not VI, V1, and this V. So what is this V? This point are the same because there are no component that consumes energy in between them. So this point is basically this point. So the voltage at point A. So VR1 is basically V1 minus VA. So that's what have been written here. And the same is also applied to I2. So I2 is VR2 divided by R2. Again, R2, what's VR2? Is V2 minus VA. Same goes for I3. It is VR3 divided by R3. And what is VR3? VR3 is V3 minus VA. And finally, if you look at I, so what is I? I is the sum of those three currents. I, the sum of those three currents. The sum of the three currents, what is it equals to? We can see that due to the properties of an ideal operational amplifier where the input gain is infinity, so we have zero currents that get into here. So I that goes into A is also the I that goes across RF. I that goes across RF. So I, what is I? I is basically VRF divided by RF. So what we have here is basically here is what represent VRF, and here is RF. So what is VRF? VRF is the potential difference between this point and this point. So this point is basically it's the same thing as this point. So it is VA, and this point, what is this point? This point uh, is the same thing as this point. So this point is basically the point of the output voltage VO. So that's why we have at the end here VRF is VA minus V output VO. So now we have the definition the definition of each I1, I2, and I3, because we know what V1 is, we know what V2 is, we know what V3 is, we know what VA is. What is VA? I think by now everyone knows that VA equals to 0. Why VA equals to 0? Because there is no current that goes into the operation amplifier. So all the currents that come from I goes to the uh, feedback resistance. So no component in the middle. So voltage at A is just 0. There's no voltage at all at the point A. So VA equals to 0. So when you do VA equals to 0, basically we simplify the equation largely. So VA equals to 0, VA equals to 0, VA equals to 0. And if we write back the KCL, so if we write back the KCL, we'll get this equation, right? So now we'll get this equation, and rearrange everything, we'll get this equation. So I, which is minus V0 over F, so basically we're left with V0, because the minus now is brought, so it is minus V0 over RF. We just leave V0 over here, and the minus over RF is now being transported to the other side, right? So we have RF here everywhere, right? So the final equation is now this equation. Now this equation. So if we look into this equation, what we can see, what we can see is basically, I'm sorry. What we can see is basically it is inverting. We have a minus, right? And then we also have an addition of three terms. 1, 2, 3. It's the addition of three terms, and in those three terms, each terms have a ratio of RF over, be it R1, R2, or R3. So that's what this is why we call it as summing operational amplifiers, right? So of course it has a gain in front of each voltages, and they sum all those voltages, and there is an inverting component, so it inverts the signal from positive to negative. And here is the case of another example. So instead of having, so previously we have V1, V2, and V3 at the input. Now we only have two input, which is VA and VB. And again, both of them are connected to each of them a resistance of RA and RB, and they are joined together at this node. So this node that we previously called as RA, right? So so it's the same thing, and we have an RF over here. The non-inverting terminal is joined to the ground, and we would like to measure the output voltage VO, V out. So here is just an addition. So basically we put RL is the resistance of the load. Usually we will leave it we will leave the circuit open, but basically here they show where it has an application where they connect it to a load directly. But that doesn't change anything in terms of calculating V output, because V output at this point is the same as the VRL, is exactly the same thing, right? So here it's written in other form. It might looks like it is a subtraction, but it is just that if we factorize everything, we would have minus. So we can put minus as a factor, and we would have the same thing as previous one. So RF over RA VA VA, sorry, minus plus RF over RB VB. So it is still a summing operational amplifier, and the minus here is just the part where it explains we put the input in the inverting terminal. So it's minus and the addition of both a VA and VB with a certain gain. RF over RA and RF over RB. So here is an example of application where, imagine if we have RF equals to 100 ohm, and RA we have 200 ohm, RB 100. So here we have 200 ohm, and here we have 100 ohm. So, and we have VA equals to VB, where both of them are 10 volts, right? So that would lead us to an output of minus 15 volts, right? Minus 15 volts. So it is an addition of 10 and 10, but with a certain operational amplifiers gain, which is RF over RA and RF over RB. So that is for summing operational amplifier. There are several other exercises that you can refer to in the slides, that you can try to do it, and if you have any question, you can ask me, right? So that is for summing operational amplifiers. So now we goes into the final is the other configuration of operational amplifier. Is the final one that we'll see in this course, in this chapter anyway. There are many more type of configuration, but these are the basic one. So the first one was the inverting, and then the next one was the summing operational amplifier, and this one is the third one, the non-inverting amplifiers. So to make it short, to cut short, a non-inverting is basically is when you put your input into the non-inverting terminals. So we have the plus terminal, the non-inverting terminal over here, and we put VI at the non-inverting terminals, right? And for the inverting terminals, we still have R1, and then a node that separates between R1, and then we have another branch where we have RF, but this time R1 is not connected to an input voltage. It is just connected to the ground, right? So let's see what happened in this particular configuration. So to understand what's happening, first we have to remember about the properties of an ideal operational amplifier. So for an ideal operational amplifier, again, the resistance, the impedance, input impedance for an operational amplifier is infinity. So there's no current that will be going into the operational amplifier. Therefore, the points here, what we call point V1 and V2 are the same. So voltage V1 and V2 are equals. And as we can see here, V2 from V2 is connected to V input, right? And V input is called VI. So V2 will be equals to VI. Therefore, V1 equals to V2 is also VI. So that's the first thing. And then the next thing, so it's written here, V1 equals to V2 equals to VI. And how do we use these properties? In order to use these properties, we'll look into the node where it's indicated as V1. In V1, again, if you apply KCL, we can say that I1, so the current that comes from R1, will be equals to I2, the current that goes into RF, because there's no current circulates into the operational amplifier. So if I1 equals to I2, then we can write, because we don't know what I1 and I2 is, so what we do is we develop I1 and I2 using Ohm law. So I1 is basically a VR1, so if I change it to a pen, so I1 is basically, it's a VR1 divided by R1, right? So here, this part is basically, it is VR1 divided by R1. So VR1, what's the VR1? VR1 is potential difference between this point and this point across R1. So this point, V at this point is basically the voltage of the ground, is the same thing because there's nothing in between. So it's 0. So this here is 0. So that's, we have 0 here. And the voltage at this point is basically the same voltage at this point V1. So that's why it's written as 0 minus V1. And what about for I2? So I2 is equals to, again by Ohm law, here we have VRF is VRF over RF. So here this portion is basically, it's VRF over RF. And what is VRF? VRF, so VRF is the potential difference between this point and this point. This point, the voltage at this point is the same thing as the voltage at V1 because there's no component in between them. So it's V1, so we have V1 here. And what is the potential, the voltage at this point? At this point, the voltage here is equals to V0 because there's no component in between them, right? So it's, at the end, is equals to V1 minus V0. So from here, we know that, knowing that previously, due to the properties of an ideal operational amplifier, we have V1 equals to V2 equals to Vi. Therefore, we can write that V1 is also Vi. So here 0, we just eliminate 0, right? So we end up with minus Vi over R1 equals to Vi minus Vo over RF, right? So that's the final equation that we have. So again, in operation amplifier, the voltage that we're looking for is VO or V output. If we rearrange the equation, we will then get VO equals to, so 1 plus RF over R1 multiplied by V in, right? So here, this 1 plus RF over R1 is the operational amplifier gain, AV, and there is no, if you can see, there is no inverting signal over here, there's no negative here, so it is a non-inverting amplifier. That's what we call a non-inverting amplifier, right? So here is a case of example. Imagine if we have R1 equals to 100 ohm, RF equals to 200 ohm, and VI equals to 10 volt. So we have that just now, VO equals to 1 plus RF over R1, if you remember well. Well, it's written over here, right? Multiply by V in, and if we replace those value, we get V out equals to 30 volt. So so this is op amp. So for a V input equals to 10 volt, we managed to get V output equals to 30 volt. So the gain is basically is 3, and there is no inverting signal. If it doesn't invert the signals, it 10 volt positive becomes also 30 volt negative. So that's on a non-inverting operational amplifiers. So now, to summarize, we've seen 3 of them. We've seen a step-by-step how do they works, right? I'll change to a pointer first. Okay, we've seen how do they work in terms of 3 particular operational amplifier configuration. The first one that we've seen is this one, the inverting amplifier, the non-inverting amplifier, right? And then the next one that we have seen is basically a summation amplifier. And the last one that we have seen is basically the first one is inverting, the next one is summing amplifier, and the last one is the non-inverting amplifiers, right? So by now we have demonstrated how do we go through the calculation by by basically applying the properties of an ideal operational amplifier, which is the main thing that you have to remember is as the uh, input impedance equals to infinity, then we can do the following calculations, the calculation that goes after that, right? So the same thing could be done for others. For example, there is other that we haven't demonstrated. For those that we have demonstrated, for example, for inverting amplifiers, non-inverting amplifiers, and summing amplifiers, we can directly use the result that have been demonstrated. But there's also others that we haven't demonstrated, but we can do it as well if you have time to do it. There's a voltage follower, so this one is really easy. What it does is basically there's not even gain. It's just the V output will be equals to V input, and then the last one that we haven't demonstrated is basically a difference amplifier. What's in difference amplifier is basically we will have a gain here R2 over R1, and in terms of input amplifier it basically deducts V2 by V1, right? V2 by V1, and this is the configuration how we actually do it. Okay, so that's all for operational amplifiers, and see you in the next chapter.